5 kW to about 25 kW. Heat pump thermostats are specially built to handle an increased number of control circuits. Both electromechanical and digital styles are available. All have emergency heat mode override. Some thermostats are combined with an outdoor thermostat. This type control allows auxiliary heat only when the outdoor temperature drops below the balance point of the heat pump. With improved capacity and efficiency, the balance point of high-quality heat pumps is being lowered with each new design. The heat pump brings with it a built-in efficiency that has made it a very popular heating and cooling system. Its popularity is not short-term. Energy from fossil fuels is limited, and their costs can only rise. The heat pump is ready to fill the need. It is a technology proven to be cost-effective and reliable. A key partner in this technology is the technician, the key to good performance in any installation.
What I'd like to know is, can we get copies?
Can we get copies?
Linux sells these tapes, and so I certainly could get the information to you to purchase one.
I think we'd probably have a copyright problem if we made copies. Well, now that you're all experts on the operation of the heat pump, let's back up a little bit and discuss manufacturer's design. There's something that's very critical about the operation of heat pumps and air conditioning, and that's airflow. And most, if not all, heat pumps and air conditioning systems today are designed on 400 CFM per ton. A very critical piece of information for you to know. There are some out there, some older train units that they were looking for 450 CFM, but that's rare. It's almost a standard in the industry. So when you're out there working on these things, you should be looking for about 400 CFM per ton. There is also two different types in the cooling cycle of cooling that are happening. You've got latent heat and sensible heat. The heat you can measure with your dry bulb thermometer is the sensible heat. And I'm sure you're out there looking for about a 20-degree temperature drop when you're checking out these systems. There's also another temperature drop happening, which is a wet bulb drop, when moisture is being condensed out of the air. So part of the work of the heat pump in the air conditioning cycle or an air conditioning system is condensing moisture. Now, you don't pick this up in your dry bulb thermometer, but it's a critical piece of information you need to know, and we'll get into it a little bit later as to how this affects the operation. Heat pump sizing. In all heat pump manufacturers designate the capacity of the machinery, and it's based on a standard, which is 95 degrees and a certain relative humidity and so on and so forth. In Tucson, however, our design temperature is 105 degrees outside in the summer, and we design to 30 degrees in the wintertime. And when you size a heat pump, you size it according to the cooling gain rather than the heating loss. The reason for that is if you're maintaining an indoor temperature of, say, 75 degrees, and we're going up to 105, there's a 30-degree difference between the inside house temperature and the outside temperature in the cooling mode. In the heating mode, if you're maintaining 75 degrees inside, and you're going down to 30 degrees outside, now you've got a 45-degree difference, so you can see that the heat loss is going to be greater than the heat gain, approximately a third more. So if you sized it according to the cooling needs, or the heating needs rather than the cooling needs, the heat pump would be grossly oversized by approximately 33%. Also, when we size heat pumps, we design to 105, and as you know, in Tucson we occasionally get higher than that. And the sizing is based on, I think, about 95%, covering 95% of the conditions. In Tucson, the weather data indicates that in an average year, the number of hours we spend between 105 and 109 degrees is only 10 hours per year. Now, you know, some years it might be 20 or 30, other years less, but on the average, and this is national weather data information, the time above 105 is really relatively few hours a year. On the other end of the scale, the number of hours that we spend between 25 and 29 is only 21 hours per year. So that's where we get our design conditions for Tucson based on national weather data. Since you size the heat pump based on the cooling needs, and the heating needs are greater, in a residential application, you need to install additional supplemental heat. Now on the tape, they said it's sized at 100%. We don't do that in Tucson. This is based on national information. If a heat pump was installed up in Minnesota, and believe it or not, they install them in Minnesota and Alaska, at a certain point, the heat pump is just as efficient as electric heat, and there's no point in putting wear and tear on the compressor. Once you get down to that point, you might as well shut the heat pump down and go straight to resistance heat. In Tucson, we don't run in those conditions, so we install just enough resistance heat to supplement rather than to carry the entire heating load. Usually what you'll find in Tucson is anywhere from 5 to 10 kW worth of supplemental heat installed in the unit. Supplemental heat can be very useful in determining whether a heat pump is operating properly, and I'll cover that point in just a little bit.
Bob?
Yes.
Just as an aside, the people in here range from Flagstaff to Sierra Vista, as well as Tucson. So we've got some changing weather conditions for some of these inspectors.
Oh, absolutely, yeah. In Flagstaff, of course, if you're dealing with a heat pump, you're probably in one of those conditions where at a certain ambient temperature, you would have a control, an outside control that would sense that and actually lock out the heat pump and go over to strictly resistance heat operation. But they work, and they will produce more heat than resistance heat all the way down into around the 0 degree range. Yes?
How many kW per electric coil typically? Is that a standardized thing?
Generally, the average kW is about 5. Now, they do make smaller resistance heaters. You can get them down in the 2 and 3 kW, 2, 3, 4 kW range. Most of the manufacturers, I think what you'll find in the field is that most of them are 5, 7.5, and 10 would be more than what we would need in any application here in Tucson. Yes?
Out in Phoenix, I don't seem to see much auxiliary heat in Phoenix.
No, you don't, and that's due to the difference in the weather conditions. The number of hours, you know, I think generally speaking, you're about 5 degrees warmer than us at any given point in time. And since you're hotter, your cooling capacity is higher, so the machine would be sized larger to begin with. And yet you have less heat requirements, so now your balance point, the point at which the heat leaving the home is equal to what the heat pump is producing, is down at a point where the machinery is going to be able to produce that volume of heat, so you don't need the supplemental heat that we do down here. So Tucson is again a little bit different story. There is really no requirement for additional supplemental heat, and it's unfortunate because it can be really a useful tool in determining the proper operation. The other nice thing about supplemental heat is that it automatically comes in during a defrost cycle. The tape mentioned defrosting, and when these machines do go into a defrost, they revert to the cooling mode and actually remove heat from the house in order to put it into the outdoor coil, warm it up, and melt the ice. If you have supplemental heat installed, this automatically turns on during the defrost cycle to temper the air. If you've got 5 kW and it's a relatively small unit, that in some cases is enough to temper the air back to room temperature rather than having 55-degree air blowing out your registers for 2 or 3 minutes while it's in the defrost cycle. you actually have room temperature air circulated, and under those conditions you probably wouldn't even notice it's in a defrost condition. I would venture to say that your primary tool for checking these things out is a good electronic thermometer. A fast reaction thermometer, if you only have one, is something that you would need to have. If you've got two and are matched, that's good because you can take two temperatures simultaneously. The whole time you're checking these things out, temperatures are changing. So a good fast reacting thermometer would be needed. I think what you're probably dealing with too is the old rough rule of thumb that you're looking for in the air conditioning mode about a 20-degree temperature differential. In other words, if your return air going into the equipment is 75 degrees, you're looking for approximately 55 degree supply air temperature. There are a number of things that can cause this to vary. Probably the number one thing is the airflow. We talked about manufacturer's design being 400 CFM per ton. If you're moving less than 400 CFM per ton, your air temperature drop will go up. If you're moving more, it will be less. Things which affect airflow, of course, are things that you're going to inspect for. Probably the number one thing is a dirtier plugged filter. If the homeowner hasn't been doing good maintenance, you could have a dirtier plugged evaporator coil or indoor coil, as in the case of a heat pump. If it's a belt drive system, you could have a loose belt. You could have a pulley that was never set up properly, where you never, the machine never did move the proper amount of air. Multiple speed systems, perhaps the thing was never set up on the proper speed, so you're a little bit short on air. Duct problems, other things that are really hard to identify. The other thing that might affect the temperature drop is the refrigerant charge. If the refrigerant charge is low, you're not going to get the drop you need. If it's overcharged, you're going to get an incorrect temperature drop. Another thing to consider, since you probably deal with both occupied and unoccupied residences while you're making your inspections, is the temperature of the house. As I said before, there's two types of cooling that are going on. One which is the sensible that you measure, and you're looking for about 20 degrees. The other is the latent cooling. If you're in a home that's vacant and the air conditioner's been off, it's a hot day, it's 95, 100 degrees in the house, you're not going to drop the temperature and get into a condensing condition. So now all of a sudden, instead of seeing 20 degrees, you're going to see 30 degrees or better, because all your energy is being put into dropping the dry bulb. So that will have a big effect on what you're going to see in the way of a temperature drop.
How long might it take for that to stabilize?
Well, it depends on the sizing of the equipment. If the equipment sizing was marginal to begin with, in other words, when you're sizing the equipment, you're going to size for that, not the worst case condition, but your design condition. And say you're sizing a unit and it comes out that it's just over a 4-ton load. You have to go to a 5-ton machine. Now you could be as much as almost 12,000 BTUs oversized. If that's the case, you've got a lot of reserve capacity, and of course when you turn the machinery on, the house will cool down more quickly. On the smaller units, you're only going to change perhaps up, be within a half a ton oversized, and you might be right on capacity. If you're right on, and it's 105 degrees outside, you're basically your machinery output is equal to the input of heat into the home, and it's sized to maintain temperature and not necessarily to make up temperature. Now, of course, it's going to run more efficiently because you're dealing with bigger temperature differentials. So the temperature will drop and start coming down, but it will take a long time to do it if the house is real warm. Yes, sir?
I've been told by other technicians and things that an acceptable drop was between 14 and 22 degrees. You're saying 20?
I use 20 as the old rough rule of thumb. There will be variations. I would say